Okay. Hi. Let's start. So this is chapter 4 of our syllabus, and it's about magnetically coupled circuits. I just added this one magnetic circuits here in chapter 4 because I will not discuss this one in E126. Uh, Before it was part of E126, but now it was removed and it's only now 2 units. So I decided to include this one in chapter 4 here in EE124. So before we go to magnetically coupled circuits, first I will discuss magnetic circuits and what are some of the principle and concepts behind magnetics before we go to some application in magnetically coupled. So I will divide this lecture into two parts, magnetic circuits, then later on we go to magnetically coupled circuits. So first, here, we have a force and a current carrying conductor in a magnetic field. I have here three formulas. The first one, this force here, Q times V as in velocity times B, the magnetic field. So when we are in a magnetic circuit, when we say magnetic, we have north, south, pole, we have electromagnetics, so it's not just about permanent magnets, but we can also produce magnetic field through electricity. So there is a very broad relationship between the two. So here, this first equation, this F equals Q V cross B. So this is the force on a charge in Coulomb, which is moving at a velocity v in meters per second in a magnetic field of flux density B. So this letter B here is flux density. V is the velocity. Q here is the charge, which is in Coulomb. This one is the velocity in meters per second, and this one is the magnetic field in terms of field flux density, which is in Tesla. I will discuss later on what is this magnetic field and how do we solve them. So here, when we have a charge flowing through a conductor and that conductor is in a magnetic field B, then inside the charge there's a force that is being experienced, and this force is equal to this one. So this unit of force will be in Newton. So that's the force on the charge. That is the force being exerted on a charge. Now, this second equation or formula, we have another two formula here which are also related. So these are just the same. This formula and the formula here is the same. And also this was derived from the first formula, because if you remember the relationship between Q and I, we know that I is dq over dt. So in other words, this is in coulomb per second. So another unit for amps is coulomb per second. And if you go back to the first formula here, Q times V, we will come up with coulomb meters per second. So if we remove this part, is actually the current, which is equal to A, amps. So instead of using the charge coulomb, we can use amps here, but you need to multiply it with m, where m will be our length. So it's related with the first equation. And this one will be, this equation or this formula will be the force on the current carrying conductor. If a current carrying conductor is placed in a magnetic field produced by, it can be a permanent magnets, or any other source of magnetic field, then the fields due to the current carrying conductor and the permanent magnets will interact, and that will cause a force to be exerted on the conductor, and that force is equal to this formula here, F equals I times the cross product between the magnetic field flux density and the vector L, or displacement, or the length of the conductor that is in the field. So we have basically three components here. We have the current in amps, we have the magnetic field density in Tesla, and we have the length in meters, length of the conductor in meters. And also here, the direction of L here represents the direction of the current, because we treat the current here as a scalar quantity, not a vector quantity. Usually we multiply it with this vector L. They have the same direction. So actually we can use, so for example, we have here a permanent magnet, north and south pole. So if we have a permanent magnets, north and south pole, between them we have magnetic field. We can produce magnetic field. Now if we have a conductor, here placed, a moving conductor, or a conductor that carries a current, and the current is in that direction of the conductor. This is I, current I. Then this conductor experience a force, and the direction of the force will be the cross product of the direction of the magnetic field and the direction of the length. So the direction of the length will be in the same direction as the current, in that direction. So what will be the direction of the force? When we are taking the cross product, it should be perpendicular to both of them. So in this direction is the magnetic field B. So where's the force? We can use left hand rule. What is left hand rule? This is your, if this is your first finger, this is your thumb, and this is your middle finger. Then the first finger, or the forefinger, will represent the direction of the current. So this will be the direction of the current. The middle finger is the direction of the magnetic field. This one is the direction of the magnetic field, and the thumb will represent the direction of the force. So in this case, if they are perpendicular to each other, if I and B are perpendicular to each other, then the direction of the force will be in that direction. It should be in perpendicular also with both of them. So we can use left hand rule when we are we want to determine the direction of the force, or you can just do the cross product. But if you don't know how to cross product, you can use this other formula here, solve for the magnitude, then later on you can use your left hand rule to determine the direction of the force. So now let's take an example. Here I have an example. An electron that has velocity v equals 2x 2 times 10 to the 6 in the x direction plus 3x times 10 to the 6 in the y direction EY, the unit is meters per second, moves through the magnetic field which is equal to 0.03 AX minus 15 EY Tesla. Now, the question, find the force on the electron, and B, repeat your calculation for a proton at the same velocity. So, solution. So what we will do here is, for letter A, we will be using the first formula, F is equal to Q, the velocity cross product with the magnetic field. Now, the Q here, because we want to solve for the force that is exerted on an electron, so we need to use the charge for an electron. So what's the charge for an electron? What's the charge for an electron? Should be equal to, it's a constant, it's on the calculator, it's equal to negative 1.6 times 10 to the negative 19 coulomb. So we will use that one. So solving for the force, so negative 1.6 times 10 to the negative 19. We multiply this one with the cross product between the velocity and the magnetic field. So the velocity is here 2 times 10 to the 6 in the x direction, plus 3 times 10 to the 6 in the y direction. Then cross this one with the magnetic field, which is equal to 0.03 ax minus 0.15 ay. Then, do you remember how to take the cross product between two vectors? So we can use here, to solve for the cross product, we can do it manually, or we can use what we did in EE126. We did use the matrix. Remember the matrix? So how do we use the matrix in solving a cross product? So first, we take the directions. Then the first vector that we should write should be the first vector on the cross product. This is not the same. V cross B is not the same as B cross V. So we need to first write the velocity 2 times 10 to the 6 in the x direction. Then in the y direction, it's 3 times 10 to the 6. And we don't have a z component, so this is just equal to 0. Then next is we write the vector B, or the magnetic field, which is equal to 0.03 in the x direction and negative 0.15 in the y direction and 0 in the z direction. Then first, copy the first column, 0.03, then the second column, ay 3 times 10 to the 6 and negative 0.15. Then we multiply them in this direction and this one. So these are all positives, downward positive, upward negative. So these are negatives. So to simplify this one, so negative 1.6 times 10 to the negative 19. Then we multiply with all the positive downward. So the ax times this one is equal to 0. Then ay times 0 times 0 is also 0. So we left with the z component, which is 2 times 10 to the 6 times negative 0.15 in the z direction. So this is positive. Then for the negative, these two are 0. So we have 0.03 times 3 times 10 to the 6 in the z direction. So we can now simplify this one. If you want to solve for the force, so the direction here will be in the z direction. Why? Because they are just like what I wrote here. If this is our y direction, and this is our x direction into that direction. Then our z will be upward direction, EZ. So it's just the z component that will remain because both of our DL or L and B or B and V are perpendicular with each other in xy plane. So the result will be either the force is upward or the force is downward. It depends on also the direction of B and V. So in this example, so if you want to solve for F now, our F will be equal to, so F here, if we calculate this one, so our F now with the direction will be equal to 6.24 times 10 to the negative 14, and the direction will be positive EZ. So this will be in Newton. So this is our force experience in our electron. So that's the force. Now, what happens if instead of electron, the charge that is passing through that conductor is a proton, meaning it's a positively charged positively charged. So instead of using QE, we use the charge for a proton. So what's the charge of a proton? It's the same magnitude as that of electron. The only difference is it's positive because it's a proton, so it's a positively charged. So it should be positive 1.6 times 10 to the negative 19 coulombs. So this will be the charge for the proton, and all the rest will be the same because on the problem says the same velocity. So if it's the same velocity and the same magnetic field, then what will happen to our force? So here, the force will, instead of negative 1.6, it will be positive 1.6. Positive 1.6 times 10 to the negative 19. And we multiply it with the cross product, which we did for letter A, for the first part. So this is 2 times 10 to the 6 times negative 0.15 in the z direction minus 0.03 times 3 times 10 to the 6 in the z direction. So if we solve for F, they have the same magnitude, but they don't have the same direction. So the direction will be a negative 1, 6.24 times 10 to the negative 14 AZ in Newton. So what does this mean? This means that the direction of the force really depends on the charge and the magnetic field. So that's the force experience in a magnetic field. Now, what if we have two conductors and they're in parallel? So parallel meaning they have the same distance all throughout. What will be the force experience between them, between the conductors or the wires that is carrying or that are carrying currents? So the force derived from the first formula will be equal to this one. Now there's a new term here, mu 0. This mu 0 is a constant term. This is equal to 4 pi times 10 to the negative 7. This is called the permeability of free space, and the unit for this one is Tesla meters per amp. Then I1 and I2, these are the currents passing through the parallel conductors. Then L is the length of the conductors, and R R here is the distance between the conductors in meters. This is also in meter. This is in amp, and this is in amp. So if we try to multiply this one, what will be the final answer? The final answer will be Newton. So the unit for force is still Newton in MKS. Later on, we can also use CGS instead of MKS. But let's try to first familiarize ourselves with MKS so that it's more clear and it's more not difficult to comprehend. So to apply this formula, so this is a constant VO. So I1, I2, 2 pi r. Let's try to apply this formula and take an example. Here, we have two infinitely long parallel lines. Wires are lying on the ground. A distance A equals 1 centimeter apart, shown in figure 4.1. So this is the figure. A third wire then of length L is equal to 10 meters and a mass of 400 grams carries a current of I1, which is equal to 100 amps, and is levitated above the first two wires. Now, at horizontal position midway between them, the infinitely long wires carry equal currents, which is equal to I2 in the same direction, but in the direction opposite with the levitated wire. Now, the question is, what must be the current in the infinitely long wires so that the three wires form an equilateral triangle? So when we say equilateral triangle, the distance between them are all the same. So if you look at the figure, this is our figure. This one is our levitated wire, and these two are the infinitely long wires, which is A distance apart, which is equal to 1 centimeter. So if it's equilateral triangle, if this is 1 centimeter, this should also be 1 centimeter and 1 centimeter. So if you observe, the conductor that carries I1 is levitating. Why? Because of the forces due to the current passing through the other wire and the current passing through it, I1. So for that to levitate, it should be in equilibrium. So if we try to add all the forces at that point, when we say equilibrium in physics, it should be equal to 0. So in other words, the forces that goes upward should be the same as the forces that goes downward. So what are the upward forces and what are the downward forces? We have a downward force here, which is Fg. This is due to gravity. This is the force due to gravity at the levitated wire. So if you want to solve that one, it's just equal to mass times the gravity. That's Fg. While here, we need to solve for the y components of FBr. FBr is the force due to the right conductor and L due to the left conductor. They have the same magnitude. Why? Because they have the same distance. So if we take the y components, we add them, it should be equal to Fg. And what current is used there to make it equal to Fg? That will be I2. But instead of using the component method, just like the normal ways we do in physics, I'll try another method, which is what we do in EE. We use complex method. It's complex. So if we use complex, first we need to plot them in the complex plane. So first, we know that the magnitude of, let's say, FBr is equal to its magnitude FBr, and the angle will be, so this is FBr. So if we plot this one in the XY plane, we need to know this angle. So what will be this angle? What is this angle? It's an equilateral triangle. It's also an equiangular triangle. So if you divide it, 180 divided by 3, this angle should be equal to 60 degrees. And if this is 60 degrees, this should be equal to 120 degrees. 180 minus 60. So the angle of FBR will be 120 degrees. And for FBL, the force due to the left one, it should be equal to its magnitude with the angle of, so this will be its angle, which is the same, it's also 60 degrees. So this is also 60 degrees. And while FG is equal to MG with the angle of, it goes downwards, it should be negative 90 degrees. So now we all know the forces acting at the levitated wire. And we also say that the magnitude of the right force should be the same as the magnitude of the left one. And we can just call this one F, which is actually equal to, if you use the formula here, mu O I1 I2 mu O I1 I2 times the length divided by 2 pi r. So mu O is a constant, 4 pi times 10 to the negative 7. We multiply this one with I1 and I2. We know I1 is given, I1 is 100 amps. I1 is 100 amps. So this is 100. And we don't know I2, we are solving for I2. And the length of the conductor, so the total length will be the length of the levitated wire, because we want to solve for the levitated wire. And that is equal to 10 meters. So times 10. Take note of the units. You need to be consistent. In meters, all in meters. No centimeter. It's all the same. All over 2 pi. The distance between them. What's the distance between them? The distance between them is 1 centimeter. That's 1 centimeter. So it's not meter. We need to convert that one into meters. So it should be equal to 0.01 meter divided by 100. 0.01. So that will be in meters. So if we solve this one, the magnitude now of the two force will be equal to 0.02 times I2 in Newton. It's only the magnitude. We need to include also the vector. We add them vectorially, not algebraically. So now, I have said before that if this is in equilibrium, if we add the upward forces and the downward forces, it should be equal to each other. Or in other words, if we add them all, it should be equal to 0. So we can say that if we use the complex method, FBR plus FBL vectorially, this should be equal to FG vectorially. So if we solve this one, what's FBR and what is FBL? BR, we know the magnitude is 0.02, or we can just put here FBR, F with the angle 120 plus F with the angle of 60, which is equal to FGM times G. What's the mass? The mass is 400 grams, or it's equal to 0.4 kilogram, and we multiply it with 9.81, the gravity. Why do we need to convert it into kilogram? Because Newton is kilogram meters per second square, and the angle here will be equal to negative 90 degrees. So we know F is equal to 0.02 I2. So that's our that's what we want to solve. If we can solve for F here, then we can now solve for I2, which is the unknown. So how do we solve F here? So to solve for F, we need to convert these two into uh, rectangular form. They are in the polar form. We cannot just add them in polar form. So we need to convert them into rectangular form. How do we convert them into rectangular form? So remember, from polar to rectangular. So R angle theta. So this is polar. So if we convert this one into rectangular, it should be x plus jy, where x is equal to r cosine theta and y is equal to r sine theta. So here we have now what will be our x. Our r here is I. So our x will be I, or f, cosine of theta, or cosine of 120 degrees. So we are converting the first one. Then plus j, our y, will be r, which is f, sine of 120 degrees. And for the other one, plus f cosine, instead of 120, it's now 60. So 60 plus jf sine of 60, and this is equal to, if you multiply this one is equal to 3.924, angle negative 90. So we can factor out f here, factoring out f, and we know that cosine 120 is equal to cosine of 120 is negative 1/2. So this is negative 1/2. Sine of 120 is, so plus square j square root of 3 over 2. Then here plus cosine of 60 is positive 1/2. Then sine of 60 is positive square root of 3 over 2. Positive square root of 3 over 2 j. And this should be equal to 3.924 angle negative 90. So if we simplify this one, and we substitute f, which is equal to 0.02 I2, to 0.02 I2 times this one, so this will cancel out, and square root of 3 over 2 plus the square root of 3 over 2, so it's just equal to square root of 3. So this will be j square root of 3 equals 3.924 angle negative 90 degrees. So now the only unknown here is I2. So if we want to solve for I2, we divide it with both sides. This is 3.924 angle negative 90 divided by 0.02. So this is j square root of 3, or this one is equal to positive 90. So if we do this one, I2 will be equal to 113.28 angle negative 180 degrees, or negative 180 is just equal to 0 degrees. So I2 is just equal to 113.28 amps. So we need the current of equal to, a magnitude equal to 113.28. This is a DC current. It should be DC, it's not AC. So that's the current we need here in both the infinity long, so that we can make the other wire levitate with the same distance as the other wires. Okay, so that is the force between two conductors that are in parallel. So next, so what we did is just for a straight line. What happens if we have not a straight line, we have a coil? So if we have a coil, then there is what we call a magnetomotive force. Magnetomotive force, it's also for not the coil, it's a straight line. It can also be a we can also have a magnetomotive force, or simply MMF. This one is the reason why we can create or produce or set up a magnetic flux around a magnetic circuit. So, or we can produce a magnetic field. So this is the reason why we have a magnetic field. It's just like the EMF in electrical circuit, electromotive force, but it's not a force. It's not a force. Just like EMF, which is not also a force, it's something that used to push the electron in EMF. Here in magnetomotive force, it's also something that tends to push the magnetic flux around a magnetic circuit. And the symbol that we'll be using is this symbol, and it's equal to N times I, where N is the number of turns. If this is a coil, this is turns, and this one is in amps. So the unit for this one is ampere turn. Or if it's straight line, if we don't have a turn, then it's just amp. So we can also say that the unit for magnetomotive force, MMF, is also equal to amp. It's just equal to the current. Whatever the current, the higher the current, the higher the magnetic field, the higher the magnetic flux produced. So this is an MKS. The other formula, this one is in CGS. This one is in CGS system. This one is in MKS. So in CGS system, the unit will not be equal to ampere turn. It will be equal to what we call Gilbert. This is Gilbert, or abbreviation is GIG. And 1 Gilbert, 1G, is equivalent to 0.796 ampere turns. So that's the conversion between them. So if you are in CGS means centimeter gram second, you use this formula 0.4 pi N times I, not just N times I. You should multiply it by 0.4 pi. So if you want to use MKS, you can use MKS, but you need to convert all your units into MKS system before we use this formula. You can just memorize one formula if you want. Then this one, MMF, produces a magnetic flux that flow through the magnetic circuit. And what is a magnetic flux? Magnetic flux is actually, these are just lines. The number of lines that is flowing through a magnetic circuit. So, for example, if we have a permanent magnet, north and south here. So, between them, there's a magnetic field. And if there's a magnetic field, there's a magnetic circuit, then there's a magnetic flux. Magnetic flux are the number of lines, these lines. The greater the number of these lines, the greater the flux, or the magnetic flux that is flowing from north to south. So that is magnetic flux, and the symbol we use is phi. And the unit for magnetic flux in MKS, we use Weber. WB. This is in MKS. In CGS, we used Maxwell's or lines. Maxwell's, MX, or lines. So this is in CGS, MKS and CGS. And the conversion between the two, 1 Weber is actually equivalent to 1 times 10 to the 8 Maxwell's or lines. So CGS, these are used in a very small scale applications, and if you go higher scale in terms of meters, then we use MKS. So in electrical engineering application, we usually use MKS system because if we talk about transmission lines, but if we talk about uh, transformers and motors, we use CGS. So magnetic flux. The first way to measure the magnetic field, we call it magnetic flux density. So it's a density, it's a unit per square unit per area of the flux. So the formula will be just equal to phi over A. So the unit for this one, magnetic flux density, I already told the unit before at the first part, B. B is in Tesla for MKS. And for CGS, what's the unit of uh, magnetic flux density? So in MKS, the unit is Tesla or T, named after Nikola Tesla. For CGS system, the unit we used, instead of Tesla, we measure this one in terms of Gauss. So that's in CGS. And what's the relation between the two? 1 Tesla is equivalent to 10,000 joules. That's the magnetic flux density. And if we want to determine the direction of magnetic flux or magnetic field or magnetic field strength later on, we can use the right hand rule. So right hand rule, the thumb represents the direction of the current, and the direction of your other fingers will be the direction of the magnetic flux density, which is usually in circular direction, circular motion. So it will be in that direction. So you just use right hand rule instead of left hand rule. So that's magnetic field density. Another way to measure the magnetic field is through its intensity, or some uses strength, magnetic field strength, or magnetic force. It's not a force, but it's magnetic force. Some book uses magnetic force. So to solve for the magnetic fields, we can use the Biot-Savart law. This one is the same or similar with the infinitely long straight line in EE126 when we are solving for the electric field. It's magnetic field, so it's almost the same. So if we want to solve for the magnetic field intensity, then we can use this one. So if we want to solve for the intensity at density or intensity at this point, so we need to solve for the contribution of all very small cuts of this line. We cut them into very small differential length. Then we solve for the effect of this one. Then later on, to determine the total magnetic field, then we just add them all. So according to Biot-Savart law, that differential magnetic field is equal to this one, mu times I times dl. The direction of dl, just like what I've said, is the same direction as the current. So it's we make dl as a vector instead of the current because we treat current as a scalar. So mu here is what we call the permeability. And that mu is equal to, later on we will discuss that one, mu naught, or the permeability of free space, times the relative permeability of the medium. So if you're talking about air, so if you have a conductor along air space, then mu here is just equal to mu naught, mu o. dl is the length, total length of the conductor. Ar, this is a vector, a unit vector. It's the direction of this vector r here. So that direction is AR. and we divide that one with 4 pi times its magnitude, the magnitude of r squared. And that is the flux density. So if we remove mu, then that's the magnetic field intensity. You just remove the mu here. It's the relationship between them. We will discuss that one later on. So it's a cross product again. So it should be perpendicular to both of them. So here. Now, if we want to solve for the total, this is just a differential infinitesimal value for the magnetic field. If we want to solve for the total, we need to add them all from a closed loop. So from length to length, from this point to this point. If you want to solve that one, you integrate them and so on. Just like what we did in EE126. It's mostly similar. And another way to solve for the magnetic field is we use the Ampere's law. Ampere's law, this is the equivalent of Gauss's law in electrostatic. We did not yet discuss the Gauss's law in the in E126. That will be our next topic in E126. Or this is also equivalent. It's just like the Kirchhoff's voltage law of circuits, electrical circuits. So if we, this right part of the equation, if we move it into the left side, or the other one move it to the right side, then it will be equal to 0. If you add them all, it will be equal to 0, just like Kirchhoff's voltage law in a closed loop. If we add all B times DL in a closed loop, it should be equal to this one. The unit for this one will be our AMF, and this is also our MMF. Times mu, it should be not that. This should be MMF on the H, magnetic field intensity. Another way to solve for the magnetic field intensity is to divide that AMF with the length. It's derived from this one. If you know the length, if it's straight line, or if you know the total length, then you just divide it to the other side, and that will be H dl. It's just a dot product. So if they are perpendicular to each other, H and dl is perpendicular to each other, then it will be cosine of 90. It should be 0. Then they should be parallel. Then another way is to take the force and divide it with phi. This is also the same with electric field. The electric field, the unit for electric field is just force Newton per Coulomb, F over Q. So it's F over, instead of Q, phi. Q is for current. Phi here, our current in magnetic circuit is phi. So the unit here will be Newton per Weber. So that's another way. Here, the unit here will be the unit for H. What's the unit for H? H is the magnetic field intensity. And the unit for that will be ampere turn per meter, because this is ampere turn for the MMF and divided with the length, meter, ampere turn per meter, or it's the same as Newton per Weber. In CGS, so this is in MKS. This one is in MKS. In CGS, the unit for H, we call it Oersted. Oersted. OE. And the conversion between the two, 1 OE